Hey there, folks. This is Mr. Young, and I'm going to just run you through some examples of half-life problems. Remember, half-life is the time it takes for half of your parent isotope, your radioactive isotope, such as this brown circle, to decay into your daughter product. So in this example, radioactive uranium, that's our parent isotope, decays by emitting alpha radiation, and it turns into thorium. And we go from something with an atomic number of 92, uranium, to something with an atomic number of 90, thorium, because that alpha radiation causes the substance to lose 2 of its protons. Now, half-life. Half-life means you start out with 100% of your parent isotope. And let's do a really simple example with something that has a half-life of 10 years. That means at time 0, at the starting time, we have 100% of our parent isotope. Okay? After 10 years, 50% of that parent isotope will have decayed to our daughter product. And so you'll see 50% of these circles will still be brown, 50% will now be the daughter product. After 10 more years, that's another half-life, we will see that we've got 25% of the circles are brown and the rest are all blue. And 10 more years, we'd get to 12.5% would be brown. And eventually you'll get so that you've eventually reached 0 of the parent isotope is left. Half decays to the daughter product every half-life. Okay, so here's some problems. These are in your notes packet from week 1 of nuclear chemistry. They're on page 8, okay? And again, half-life, the time needed for half the atoms of a radioisotope sample to decay or undergo transmutation. To do any of these problems, you don't need a formula. All you need to do is be able to write a little chart like this. If you start with 1 whole, then after 1 half-life, you've got a half of that. Half of that becomes a quarter after the next half-life. Then it becomes an 1/8 after the next half-life, 16th, 32nd. That's about as far as you'll need to go. So let's walk through some of these questions. Question A is really actually just very simple. Well, in A, B, and C, they're asking how much time will it take for each of the radioisotopes below to decay to the fraction of the original amount indicated. So cesium-137, they want to know how long will it take for some amount of cesium-137 to decay until only half of it is still left as radioactive. Well, really, that question A is just asking what's the half-life of cesium-137. Where did I find that? I found it on Table N. Table N lists the half-life and the decay mode of a whole bunch of different radioisotopes. Okay, the next one you actually have to do a little bit of thinking. Carbon-14. For carbon-14, they want to know how long will it take for carbon-14 to decay so that you have 1/4 of your original left. So you make a little chart. You start out with 1 whole, and then after 1 half-life, you've got a half of it, and after another half-life, you've got a quarter of it. So that is 2 half-lives. Now, here's what a mistake students make. They look at a little diagram like this and they say, oh, it's 3 half-lives because I see 3 numbers there, 3 fractions. No, we're counting the hops in between. So at 0 half-lives, we've got 1 whole. After 1 half-life, we've got a half. After 2 half-lives, we've got a quarter. So we're counting the arrows, we're counting the hops, and that means you take 5715, which is the half-life of carbon-14. This number came from Table N, times 2. 5715 plus 5715 makes 11,430 years. What about hydrogen-3? That's a radioactive isotope of hydrogen. Find it in Table N, but first make your little chart. We start out with 1 whole, then it becomes a half, then it becomes a quarter, then it becomes an 1/8, then it becomes a 16th. So it takes 4 hops or 4 half-lives to get down to 1/16th of your original amount. And for hydrogen-3, that's 12.31 years for 1 half-life times 4 half-lives. 1, 2, 3, 4 hops. 4 times 12.31 years equals 49.24 years. Next example, if we start with 100 grams of cesium-37, how much will be left after 60.4 years? How much will still be radioactive? Okay, the half-life of cesium-137, we already looked it up, it's 30.2 years. This comes out of Table N. Then we say, okay, well, 60.4 years is how many half-lives? Oh, well, 30.2 plus 30.2 equals 60.4. So we're talking about 2 half-lives here. So if we start with 100 grams of cesium-37, how much will be left as still radioactive after 2 half-lives? We start with 100. After 1 half-life, 50 of it is still radioactive. After another half-life, 25 of it is still radioactive. So the answer is 25 grams will still be radioactive after 2 half-lives. Final problem. The half-life for alpha decay of radium-226 is 1,600 years. How many years must pass until a 65-gram sample of radium-226 has decayed to 4.0625 grams remaining? So they want to know how long is it going to take, how many half-lives and or how many years will it take if you start with 65 grams and it decays till you only have 4.0625 grams left. You probably need a calculator for this. First thing you do is make your chart, but instead of 1 to a half to a quarter, or 100 grams to 50 grams to 25 grams, we're starting out with 65 grams. So we'd make a little chart like this. 65 grams, after one half-life, half of that is 32.5, half of that is 16.25, half of that is 8.125, half of that is 4.0625. Hey, we hit the target. Count the hops. Again, the common mistake students make is they say, oh, these are 5 numbers, so that's 5 half-lives. No, it is 1 half-life for the first hop, 2 half-lives, 3 half-lives, 4 half-lives, 4 hops, 4 arrows, 4 half-lives. It's 1,600 years for 1 half-life, so 4 times that is 6,400 years. That's this set of examples, and thanks for watching.